Hello, Algebra 2 students. Today, we're going to be working with more probability. We're going to be working with probability of multiple events. Okay? We're going to be working with things, a couple different definitions: dependent events, independent events, mutually exclusive events, so on and so forth. And our objective is going to be to find the probability of an event A and B occurring, and to find the probability of an event A or B occurring. So if we look here, we have these two things. Basically, you can see that this is given things from a deck of cards. And what do you notice? What do you wonder? Maybe pause the video and write down a couple observations. But you might notice that on the left here, there's hearts and there's kings. And if the event is hearts and the event is kings, you'll notice that there's a little bit of overlap because there's a king that is also a heart. Now on the right, there's two events, aces and kings, and well, they don't overlap. There's no ace that is also going to be a king. We would say that the things on the left are not mutually exclusive, and we would say that the things on the right are mutually exclusive. And we'll talk about that later. But the key idea today of what we're going to be doing is we want to find the probability of two events occurring together. And when we do that, we have to decide if one event affects the other event. Okay, so, well, we'll write a couple of definitions. A dependent event is when the occurrence of one event affects how a second event can occur. An independent event is when the occurrence of one event does not affect how a second event can occur. So dependent means that one event affects the other. Independent means that, well, they don't impact each other. So, for example, if I'm drawing from a deck of cards, actually, never mind, we'll get to that example in a little bit. So in these examples here, we'll go through a couple instances where we have a dependent or an independent event. So I want to know, are the outcomes of each trial dependent or independent events? Okay, if I roll a number cube and then a spinner, so if I roll a dice and then spin a spinner, is that going to be an independent event? Are those independent events or are they dependent events? Well, if they were dependent, they would have to impact each other. Does me rolling a number impact what happens on a spinner? No, so these would be independent events. They're independent events. Okay, now, however, if I'm drawing a card, or if I'm drawing two cards from the same deck, well, I draw one card and then I draw another card from the same deck. Does my drawing the first card impact what I can get in the second card? And you might think no, but technically it does. If I draw a card from a 52 card deck, well, I'm left with 51 cards, and well, my second card can't be what my first card is. So yeah, the first event does impact the second event. We would say that these are dependent events. They're dependent events. And the reason that is because, well, the first card you draw impacts the second card, right? So they are dependent events. Okay, that's just kind of an example of what those terms mean. So, before we get to the definition of finding these things, we're going to kind of see if we can find them intuitively. And then we'll come up with a rule for finding the probability of two events. So, we have a picnic. There are 10 diet drinks and 5 regular drinks. Okay, so there's a cooler with drinks. There's also a container that has 8 bags of fat-free chips. I don't know why. And then 12 bags of regular chips. We want to know if we grab a drink and a bag of chips without looking. We're living on the edge today at this picnic, apparently. We want random things. Well, what is the probability we get a diet drink and a fat-free chip? Okay, well, let's look at these events. Are they independent events? Does my drawing a drink impact my drawing a chip? Well, if I have drinks in a cooler and chips in a thing, the drink I choose shouldn't impact the chip I choose. So these are independent events. These are independent events. So, well, what is my probability then? What's my probability of a diet drink? I'll abbreviate that with DD. What's my probability of my diet drink? And remember that for probability, we want the total number of outcomes. Well, how many total drinks are there? There are 15 to choose from. Of those 15, how many are diet? 10. So my probability is 10 over 15, or 2/3, which is equal to, well, 66%. But 66.7%, I guess. Okay, so that would be my probability of getting a drink. What's my probability, then, of getting a fat-free chip? Well, my probability of getting a fat-free chip is given by, well, how many total chips are there to choose from? And we have 8 fat-free, 12 regular. That makes a total of 20 chips. Of those 20 chips, 8 are fat-free. So my probability of randomly choosing just the fat-free chip is 8 over 20. That's going to be the same as, well, you can divide both of these by 4, and you will get 2/5. All right, now, what we can do here is think about this before we move on. I guess I kind of gave it away right there. If the probability of drawing a drink is 66%, and I guess 2 divided by 5, that's the same as 4 divided by 10, that's about 40%. Okay, well, if that's the probability of those events independently, what's going to happen together? Well, if the probability, let's think in terms of this drink, the probability of drawing a diet drink is 66%, and the probability of drawing a fat-free trip is 40%, should I have a probability that's higher than either of those? Like, should I have a probability of 70% of drawing a fat-free chip and drawing a diet drink? Then you would probably say no. And to think in a different example, one that you're really familiar with, if I have a coin, and I have, well, heads or tails, you know from experience that the probability of getting heads is given by, well, it's just 1/2. We know it's a 50% chance. What's my probability if I flip it twice of getting heads and then heads again? So basically 2 consecutive heads. And I guess think of it like this. Should I be more likely to get heads twice in a row or less likely? And you would be saying you're probably less likely to get heads twice in a row than just getting a single head, right? So what it's going to be is, well, the probability of this event, 1 and 2, times the probability of getting heads again, times 1/2, that equals 1/4. So to find the probability of 2 independent events that do not impact each other, the probability of finding independent events is by multiplying their probabilities. So the probability of getting a diet drink and a fat-free chip is given by multiplying their probabilities. This is the same as 2/3 times 2/5. Well, that's going to give me 4/15, which is about 26.7%. I'm going to double check that my math is right there. Yes, we are good. So, to find, this is the key concept here, to find the probability of independent events occurring together, so if A and B are independent events, then the probability of A and B occurring together, for example, we had a diet drink and fat-free chip occurring together, well, that's going to be equal to the probability of event A times the probability of event B. So the probability of our diet drink and probability of our fat-free trip, drawing those together, is going to be the same as multiplying the probabilities of each of those events on their own. Since they are independent, since me drawing a drink does not impact the probability of me drawing a chip. They're independent events. Okay? And more specifically, mutually exclusive events, they're 2 events, I guess, in a slightly different context when we move on from that example. Mutually exclusive events are 2 events that cannot happen at the same time. There are events that cannot happen at the same time. Like, let's say the probability that it is freezing outside and also 70 degrees, well, those are mutually exclusive events. It can't be freezing outside, literally 32 degrees. It can't be freezing and 70 degrees Fahrenheit at the same time. Those are mutually exclusive. Okay, so they're 2 events that cannot happen at the same time. Well then, what is the probability of A and B occurring if A and B are mutually exclusive? So this is a weird way of saying something, but basically what we're saying here is, what is the probability A and B occur together if A and B are mutually exclusive, if A and B can't occur together. Wow, I'm struggling with my brackets here. That's a little better. Basically, A and B are mutually exclusive. That means A and B can't occur together. Well, the probability of an event occurring together, if they can't occur together, is obviously going to be 0. It's a 0% chance. It's like the same thing as saying, if it's 70 degrees out, what's the probability that it will freeze if it rains? And the answer is 0. If it's 70 degrees out, it's not going to freeze when it rains. At least it shouldn't, right? Okay, so we're going to go over a couple examples of mutually exclusive events and non-mutually exclusive events. Okay, so remember, mutually exclusive means they cannot occur at the same time. So let's say I'm rolling a die. Let's say I'm rolling a single die. Well, rolling a 2 and a 3. If I'm rolling a single die, can I roll a 2 and a 3? Are those mutually exclusive events? They sure are. That's a mutually exclusive event. I cannot roll a 2 and a 3 at the same time on a single dice. Okay? However, what if the question changed? What if it said, well, what's the probability of rolling an even number and a multiple of 3? Can I roll an even number on a number cube on a dice, and 6-sided die? That's also a multiple of 3? And the answer is yes, you can. We know, well, 6. 6 is an even number. And it's also a multiple of 3. Six is an even number that's a multiple of 3. Well, if they can occur at the same time, we know they're not mutually exclusive then. So this is not mutually exclusive. These two events can occur simultaneously. I can get an even number and a multiple of 3. Okay. So, let's move on to an example here. At a high school, a student can take one foreign language class each semester. So they're only allowed to take one foreign language class each semester. So about 37% of the students take Spanish, 15% of the students take French. We want to know, what is the probability that a student chosen at random, any student in the class, in the school, is taking Spanish or French? So let's just set up a couple things we know. We know, well, we know that they're independent. So we know that there's no overlap. Remember at the very introduction, we had a Venn diagram of kings and hearts, and there was overlap because there was a king that was a heart. Well, why is there not going to be overlap here? And the answer lies here. Since they can take one foreign language each semester, well, if I have kids taking Spanish class and kids taking French class, if they can only be in one of those, there should be no overlap unless someone's breaking the rules. There should be no student that's in both of those. And since that's the case, we can kind of think about these probabilities. Well, what's the probability that a student is taking Spanish? And the probability that a student is taking Spanish is 37%. Okay? We can write that as 37 over 100. Let's just say there's 100 total kids. And kind of think of it like that. Well, of the 100 kids, 37 are taking Spanish. The probability of Spanish is 37%. You can also write that as 37 over 100 too. That's another way to think of it. But let's actually think like there's 100 total kids. That makes a little bit more sense in what we're about to talk about. Okay, the probability of a kid taking French is going to be, well, 15% of those students, or 15 over 100. So if there's 100 total kids, we want to know, what is the probability that a kid chosen at random is taking Spanish or French? This is what we want to know. What is the probability of there being Spanish or French, right? Well, how many kids are there to select total? Well, there's 100 total kids. Of those 100 kids, what's the probability that they're taking Spanish or French? And the answer is, well, 37 plus 15, right? If 37 kids are in Spanish, 15 kids are in French, that gives us a total of, that would be 52 kids, right? So there should be 52 kids out of 100 in a foreign language class, which means that the probability of S or F should be 52 over 100, which is 52 Now, the reason it was important that there was no overlap is because we know that there's 37 unique kids taking Spanish, there's 15 unique kids taking French. There's no overlap. Okay, so we can just add those together. And we're going to come to that definition soon enough that the probability of, the probability of A or B occurring, you can add them. However, what would the problem be if they could take Spanish or French? Could I then just add the total kids in the class, 37 plus 15, if there could be kids taking multiple of them? And the answer is no. You have to account for that overlap. You have to account for the kids that are going to be in both of them, if that were the case. If that were the case, you'd have to account for the kids that are overlaps. You'd have to subtract however many kids you're counting, or however many kids are in both when you add them, so you're not counting kids twice. And that's where we come with this definition here. That the probability of an event A or B is given here. The probability of A or B is the probability of A plus the probability of B. If you want to think of our French and Spanish class, we found that by adding the French and Spanish kids, minus the probability of A and B. So let's go back up to our example here. If we were finding the probability of Spanish or French using this idea, well, it would be the probability of A, the probability of Spanish, plus the probability of French, minus the probability of Spanish and French. And let's think about this. Well, what's the probability of Spanish? We know that that was 37%, right? Yeah, we know that that was 37%, or 37 over 100, plus the probability of French was 15 over 100. What's the probability of a kid being in Spanish and French? Okay, well, we know that Spanish and French are mutually exclusive. Can I have any kids that are in Spanish and French, given that they can only take one foreign language class each semester? Well, I shouldn't have any kids that are in Spanish and French like we have here. So technically, I'm subtracting 0. All right, and we'd be fine just with that. Okay. So you could always use this formula. We see if A and B are mutually exclusive events, like Spanish and French were in our example, then it's just going to be probability of A plus probability of B. If you were going to try to memorize a formula, I would memorize this one. You can use this for mutually exclusive or even non-mutually exclusive events. And the reason that is because if you're doing mutually exclusive events anyways, like we did here, the probability of taking Spanish and French, well, this is just going to be 0. So I'd recommend just use this formula every time. You'll never have to worry about whether you mess it up. You'll just have to consider, well, are these two events mutually exclusive or not? If they are mutually exclusive, we know that they can't occur together. We can't have A and B, so it's just going to be 0 anyways. So that's a good thing to remember. But this is how you would find the probability of A or B. And we'll move on to one more example here. So let's say we have this bag, and we're going to select a ball at random. What is the probability that the ball is a larger ball or orange? Larger ball or orange. So we're saying, what is the probability of getting a... What is the probability of getting a larger or orange ball? What is the probability of getting a larger or orange ball? Now you can very easily find that by counting. The probability of getting a larger orange ball, well, there are 1, 2, 3 large balls, and there's how many orange balls? There's 1 orange ball. So there's 4 options we can choose. We're going to assume that they're all equally likely to be drawn. That doesn't really make sense if one's larger or smaller. You could kind of know. But assuming they're randomly drawn, well, there's 4 in which we could get a large or orange ball over a total of how many? And we have 1, 2, 3, 4, 5, 6, 7 total. Should be 4 sevenths. That's easy enough to do, but let's think this through in the way that we use this formula. We know that the probability of an event A or B occurring, in our case it's large ball or orange, is given by finding the probability of, well, a large ball plus the probability of an orange ball minus the probability of getting a large and orange ball. So let's go ahead and find those things. What's the probability of getting a large ball? And the answer is, well, there's 1, 2, 3 large balls out of a total of 7. That's a 3 in 7 chance. What's my probability of getting an orange ball? Okay, well, there's 2 orange balls, so that's 2 in 7. And what's our probability? We want to get rid of those events that can happen twice. And the reason that's important is because, well, is drawing a large ball and an orange ball, are those mutually exclusive? And the answer is no, they're not mutually exclusive because we can draw an orange ball that is a large ball. So it wouldn't just be, the probability of large or orange wouldn't just be 3/7 plus 2/7. Because that would be 5/7. But is there a 5 in 7 chance that we would draw a large and an orange, or excuse me, a large or orange ball? And the answer is no, because there's 1, 2, 3, 4. We have to account for the overlap. We are not accounting for that orange ball that is large. We're not accounting for that large and orange ball. So we need to subtract that probability, which is, well, the probability of a large and orange ball is, well, how many large and orange balls are there? It's 1 in 7. Okay, so we're not doing just 3/2 plus 2/7. We have to account for the overlap. We have to account for the overlap that occurs with this large orange ball, so we have to subtract 1/7 as well. So we get 3 plus 2 minus 1/7. Well, how many sevenths is that? 3 plus 2 is 5 minus 1. That's 4/7, like we said in the beginning. You might be thinking, Mr. Wynant, we just found it in the beginning. Why do we have to do this? The answer is you're not always going to have an easy represented problem that you can just look at and count. You're going to want to know how this works with mutually exclusive and non-mutually exclusive events. And my suggestion to you is to just always use this formula we highlighted in blue because, well, in this case, was drawing a large or orange ball mutually exclusive? And the answer was no, they're not mutually exclusive, so either way we have to use this. But even if they were mutually exclusive, like in our Spanish or French class, where the event of a kid being in Spanish and French was mutually exclusive, just remember that if they're mutually exclusive, well, what's the probability of them happening? What's the probability of having a Spanish and French student if they can't be in Spanish and French at the same time? And the answer is 0. So always just use that formula. Keep in mind that, well, if it's mutually exclusive, the probability of those events happening is 0. And that's all we're going to cover in our notes today. So if you do have questions, make sure you're emailing me or you're hopping on to those Zoom meetings. And that's all we're going to have time for today. I guess we hadn't used a lot of time. That's all we're going to cover today. So as always, have a good day, everybody, and stay safe out there.